Hello, good morning. So today we will have a seminar. We are streaming this seminar live, so we have people remotely. So I'm asking people at home if you can hear me well.
Yes, yes.
Yep.
Great. Can you see me? Because we have a camera here in the room. I'm not sure if you can see me or not.
Yes, we can.
Yeah, we can see you.
Okay, great. So we will wait a couple of more minutes for more people to join in, both at home and here in the classroom. Okay. So today the seminar will be given by Eliseu. Eliseu is a researcher here in the digital ethics field, and his research focused greatly on machine learning application in cyber physical production systems. Okay, so for you who are developing projects about cyber physical systems and you are trying to understand how to apply machine learning, what are the main use cases, so on and so forth. So Eliseu will talk a little bit about that, about his experience in multiple research and innovation projects. Okay, and at the end, feel free to engage and make the questions that you need. And if we run out of time, I'm sure you can still reach out to Eliseu. Okay, he's around here, so no problem at all, and he can help you in any way that he can. Okay. So for this seminar, the title is Applied Machine Learning for Smart Manufacturing, from predictive maintenance to process automation and optimization. Okay, so Eliseu, more or less 40 minutes, ideally, and then we open the floor for some discussion and questions. Okay. Thank you very much. Feel free to start.
So I just stopped because we were online, I believe. So continuing, we are a research lab of applied research in industries. We work in these three main areas of robotics, IoT, and algorithms applied to the industry. And today I'm here because, as you know, your course is about
Yes.
Yes.
Hey guys, sorry, can you hear me again?
Now, yes.
Yeah. So I'm not sure what happened here, but we lost connection to the microphone. So we had started already, and you didn't hear. So sorry about that. So maybe we'll start from the beginning. Sorry again, and yeah, I will be on the chat. So if you have any issues or something, just let me know in the chat. I will be monitoring that. Okay, thank you.
Okay, so maybe we'll start because, as I said, I'm a researcher in the digital lab. So it's regarding digital and industry intelligent lab. So we work mainly in three areas: the areas of robotics, the areas of IoT systems, and the areas of algorithms applied to the industry. Most of the research that we make is applied research. And today I'm here to show you some use cases because this course is about IoT and cyber physical systems. So you develop IoT systems to collect data from some process. And basically here I'm providing you some use cases about what you can do with the data that you collect. So for being not just collecting data, but providing information for the users of that system to use that data and to get more information about that data. So my presentation is split into different parts. I will start with a brief introduction of some systems that we use to digitalize the processes. So systems that we use to collect some data from the shop floor. Then I will share with you some use cases about the usage of that data, so to provide better decisions in the industry, mainly regarding these three topics of predictive maintenance, which is basically trying to predict when a machine or a component from the machine will fail from the data that we collect from that machine, from the sensor data that we collect from that machine. Then algorithms for process optimization. So how we can optimize the industrial processes with the data that we collect from the shop floor. And finally, some algorithms regarding zero defects manufacturing, which is an area of trying to reduce at the maximum the waste that industries generate and try basically to have the machines working properly, to avoid defects and try to avoid these defects as much as possible. So starting with digitalization, we at the lab we developed this solution called GECO, that stands for Gravity Inspired Environmental Condition Observer. That is an IoT device that is based on the ES32, which is a kind of board that probably you can use in this course. And in this initial project that we developed, we aim to develop a solution that would be easy to install in an industrial machine, let's say. So it's just to plug it to the machine and start collecting data in order to avoid to have some intrusive systems that requires to stop the system to install the monitorization system. So this is regarding one of the main limitations that we have in industry. That is basically when a machine is working, people from the factory don't want to touch the machine. They want basically that machine could not have new systems and not have someone programming it again. So in order to avoid that and to facilitate the adoption of these kind of systems, we developed this solution that is not intrusive to the machine currently. So it's just plug it and we are able to start collecting data about the vibration. In that case, currently we have a sensor of vibration, and we have an interface by Bluetooth that allows us to interact with the device. So we can basically start communication, stop communication, as you see the terminal on the right side. So we can start communication with a certain sample rate, and with that start acquiring some data. As next steps, we aim to add some new sensors to the board, like temperature, humidity, so we can basically start collecting more data, more environmental data, and basically implement also the interface for Wi-Fi to communicate also via Wi-Fi and not just by Bluetooth. The second project that I wanted to present to you today is regarding Dinosaur. That is a tool that fits on the next level. So we have the IoT devices like the GECO, as I presented before, and in the next level we can have a platform like Dinosaur that is currently it's a runtime environment that allows the execution of function blocks. These function blocks are tasks of software. So basically, I can use graphically, I can program the system as you see on the top on FortiAC IDE. So I can program the entire system there and then deploy the system to a distributed cyber physical system. So I can have multiple Raspberry Pis. I can program the code of each Raspberry Pi in FortiAC and then deploy the code to each one of them. This is a project that is available online on the following link, so it's open source. It implements function blocks in Python, which facilitates the implementation of machine learning algorithms and data analytics algorithms. So we can have function blocks to collect the data and then function blocks to process that data using the most used algorithms in the community. And it has also OPC1 integration, that is one of the main protocols used in industry. as use case of dinosaurs, we have these two use cases. On the right side, you can see the most common use case, where we have the monitorization of a robotic arm that is built using servo motors. So basically, we have here 3 function blocks. One function block that interfaces with an Arduino that is collecting data from the voltage, the current, and the power of each of the motors. So we are collecting that data, and then that data feeds an algorithm that predicts if the robotic arm is colliding with some object. So imagine if the robotic arm is colliding with some object, we will have a high value of current and voltage, and because of that, the algorithm can detect that type of collision. And so this is the second function block that detects the collision, and then we have a separated function block that is the green one that is executing in another device that makes the control of the robotic arm, that in case it receives a message of collision, stops the robotic arm workflow. So basically, this is the typical pipeline that we can implement with Dinosaur, where we have a distributed system. So we have these 2 function blocks executing, monitoring the system, and we have the third one controlling the system. So we have a distributed system, and we are able to program that kind of system with Dinosaur and Fortran. The second one, regarding the controlling of a robotic arm. Here we have 2 different types of function blocks. One function block that controls the gripper, that tells the gripper to open and to close, that is the blue one. And the purple one basically tells the robotic arm to go to a particular X, Y, and Z position. So we specify the position of the robotic arm, and basically using function blocks, we can orchestrate the workflow of the robotic arm. In that case, the robotic arm is basically picking and placing an object. So it's getting the object, getting it up, and putting it again down. So we are programming and workflow of this robotic arm. Another interesting project about digitalization is regarding this project, Smart Cut project, where we apply the concept of a digital twin, which in that case was a simulator that we built to allow operators to train to perform some operations. So this Smart Cut project was regarding the development of this digital twin of this simulator for operators that work on the forestry industry. So I don't know if you know, but Portugal has a large forestry industry. So mainly in Castelo Branco and in places like that, they produce a lot of wood from eucalyptus and other trees, and basically they have machines, industrial machines, to cut these trees, basically, and process these trees. And in that project, we built a simulator based on the concept of a digital twin. So the operators could train before going to the real machine, so they can train the operations before they went to the real machine. We developed a second digital twin also In that case, for performing predictive maintenance, so we can basically check when the machine was good and was not good. So we can basically monitor the status of each of the machines. So one was basically to have a simulated reality, so the operator could run, and the other was basically an operational one, so we can monitor the state of the machine. So we collect different data from different sensors, and using that data, try to predict when some components were degraded from the process. So moving on from the part of digitalization to the part more of the algorithms and of the use cases that we can do with the data that we collect from the shop floor. First use case that I will present is regarding predictive maintenance. So we have three different types of maintenance. We have preventive and corrective maintenance, that is basically the type of maintenance that we do with our car. For instance, when we change the oil every 5,000 or 10,000 kilometers, we are basically performing preventive maintenance on the car because we have a fixed schedule to make that maintenance. So every 10,000 kilometers, this is the type of preventive maintenance that we can make in a particular machine or in a particular component, such as the motor of a car. The corrective maintenance is the opposite. So we just perform maintenance when something breaks. So imagine we have a problem in the car and we go to the mechanic to perform the maintenance of that problem. That is corrective maintenance. So, and in both of these two types of maintenance, we have higher costs because if we make preventive maintenance, we are probably sometimes making maintenance when it's not needed. So, for instance, it can pass 2 years from the last maintenance, but it could be not needed to make that maintenance. And in the case of corrective maintenance, it is complicated and from the user to perform corrective maintenance, and it has a higher cost because you will have your machine stop, or if your car breaks and you don't need the car to do something or to go to someplace, you have a cost of not being able to use the component. So that is another bigger cost that we have. So these two types of maintenance, preventive and corrective, have two higher costs. So for that, we have a third one that is predictive maintenance. That is, we want to predict based on data from sensors like vibration sensor, temperature, humidity. So we can check if we have some deviation on these sensors, and we have some deviation, or when we predict some deviation, to perform maintenance in order to avoid wasting components, let's say, with preventive maintenance, and not having stocks, downtimes with corrective maintenance. So predictive maintenance aims to minimize these costs and aims to optimize the maintenance scheduling of a particular component. So one of the projects where we developed these kinds of systems was the Reclaim project, where we developed systems, a system basically to predict when we need to replace a particular component. Here, in the use case that we worked on was regarding that robotic arm. So that robotic arm is from an industry where we worked on, that was with Gorenje, that is basically a manufacturer of white goods like fridges, washing machines, dishwashing machines, televisions, things like Bosch and basically other manufacturers of these white goods. So in that process, it is manufacturing the tube of a dishwasher. So a dishwasher has a tube that is inside. So basically, you have a metal sheet. You have two metal sheets, one with a U shape, another with a L shape, and then you weld both sheets of metal. So we have basically the tube of the dishwasher. Here, the robotic arm is welding some components to put some tubes in the metal sheet of the dishwasher, and basically that industry, they after a number of operations, you need to replace the electrodes of the welding rod. So this welding rod has a component that degrades over time. So this component, with the number of weldings, gets degraded, and basically, if you replace it too early, this component, you can be wasting this material. That is a very expensive material. And if you replace it too late, you can have defects on the dishwashers that you are manufacturing. So you have this kind of problem of finding the optimal time to replace the electrode. So for that, we developed an algorithm that collects data from the electrode, from the welding process, data about the welding current, the temperature, number of operations that it made. So, and with that, it predicts the remaining useful life of the electrode. So we are predicting the number of cycles that lasts on the electrode. So basically, here on the dashboard, on the bottom, you can see the number of remaining cycles. So this is the number of weldings that remain on the electrode before you need to replace it. And most of the time, these electrodes lasts like 2 weeks. So every 2 weeks, you need to perform this kind of maintenance. And basically, with this algorithm, you are able to plan more properly that maintenance of that electrode. Besides the prediction algorithm, we have a second algorithm that is regarding the optimization of the maintenance. So basically, we have multiple robots like that. We have not just that one, we have like 10 robots like that in that part of the line. And basically, we have the second algorithm that is an optimization algorithm that finds the optimal time to replace most of the electrodes that we have. So we've got this way we have the ability to stop the line without stop the line just to perform maintenance with one robot. So we can perform maintenance with multiple robots and check which ones have less health. So we can basically perform maintenance in those robots that have less cycles of welding. The second project that I have here where we developed basically an algorithm for predictive maintenance is regarding the Intech project. That is basically a project with a car manufacturer with Stellantis, that is a big car manufacturing and has a factory here in Portugal, in Mangual. They have a factory in Mangual, and basically in the factory they have batteries that are autonomous vehicles that transport the components for building the cars. So imagine you have different stations, and then you have AGVs, these autonomous vehicles, that transport some of the components for the operators to mount the cars. And these autonomous vehicles have a battery, and this battery, in that case, was not a lithium battery, it was another type of battery, an older one. These batteries have problems. They degrade over time, like the batteries of our cell phones. And in that algorithm that we developed, we aimed to predict when we need to replace a battery. So over time, the battery gets degraded, it starts having degradation, and we wanted to identify when this degradation was higher, so we can replace the battery of the autonomous vehicle. So for that, we monitor different variables like voltage of the battery, and we develop a solution that looks at the charging curve of the battery. So when the battery is charging, we are collecting points about the charging of the battery, and then we have a curve of an ideal charging of the battery. And when the curve starts sliding from the normal, we raise an alert to replace that kind of battery. So we can see on the figure on the image of the middle some examples of the charging of graph of the charging of the battery. It has different types of graphs, plots, and on the right one we can see the different clusters of the types of charging of that battery. Some of them have defects, others have normal execution of the charging of the battery. Also, within the Intech project, we have another development that we made. This time not related with predictive maintenance, but more related with process optimization. So, as I told you before, the Stellantis production plan has different stations where the operators made some operations in the car. So in one station they add wheels, in other station they install the seats, in other station they install the mirrors of the car, and they produce different types of cars. For instance, there they produce the Peugeot Partner, the Citroën Lingo, different types of cars, and some cars are commercial ones, others are familiar ones. So they have this variability of cars being produced. And this is the diagram of their mounting line. So where they mount basically the components in the car. So it has a U shape. So it starts on the left side, then it goes that direction, performs the turn here, and then the cars left again on the left side. So it has these many stations. So each one of these points is a station that they have in the mounting line. And basically imagine, for instance, if they produce a sequence of cars that has, for instance, 3 cars that require too much work. Let's say if I produce 3 cars that have that require too much work from one of the stations. Since this is a sequential production line, this would cause delays. Basically, I cannot perform my work before the operator because the operator before was not able to finish the work that he has done. And because of that, we aim to develop an algorithm to optimize the sequence of cars. So basically what we do, we aim to optimize the sequence of the cars. So we avoid that some stations get delays because they have to work a lot in a short period of time. Because imagine if I have, let's say, 3 supervisor labels that require a lot of work from the person that puts the wheels, I don't want to have these 3 cars in a sequential way. I want to have like a supervisor label, then a Peugeot partner, then again a supervisor label. So I avoid the operator to feel the operator to have a lot of work and delay the entire process. Because if an operator is delayed, the entire process gets delayed because this is a sequential production line. And in order to avoid these delays, we develop an algorithm to optimize this sequence of cars. Because there's a lot of cars that cannot do this manually. An algorithm, they produce by day like 300 cars. So for that, we have a simulation model and an optimization model. Regarding the simulation model, it gets the sequence of vehicles that we have. It has the information about the distributions of the time that is spent in each of the stations, depending on the car that is being produced. And with that information, it simulates the times for each one of the stations. And secondly, we have an optimization algorithm that uses that simulation algorithm to optimize, to find which is the optimal sequence that produces less delays. So we can have basically the best sequence of vehicles that will produce less delays. And basically to visualize that, we have this graph because these are the graphs of the delays of each car that each car causes on the line. And the goal that we have here is to put this line more close to 0 as possible. So we can reduce most of the delays, so we can have the cycle time of the fixed cycle. Moving on, the next topic is regarding the automatic reconfiguration of the cyber physical system. So as we see before, Dinosaur allow us to orchestrate a distributed pipeline of function blocks, as you can see both in the diagrams of the right and left side. So we can have function blocks associated to different devices of the production line, like the Raspberry Pis or the PLCs that we have on the final computers. And the goal here is to optimize the allocation of tasks to those devices. Because, for instance, imagine that one of these devices breaks. If one of, for instance, of the Raspberry Pis breaks, the line stops because I'm not able to execute the software that is on the Raspberry Pi if the Raspberry Pi breaks. But if I have an automatic system that reconfigures the line, so when I detect the Raspberry Pi that is breaking, I reconfigure the line, so I put the software that is executing on Raspberry Pi in other device. This way I can maintain the execution of the entire distributed system. This is also useful when you have like a mixed production system. So when you produce different types of products, because some tasks can have variable computational requirements. So one of the tasks can consume more RAM in a particular time, and in another time it consumes less resources. And because of that, in some periods of time, it would make more sense to execute those tasks in a different device. So regarding that, we developed a system that basically maps the pipeline into a graph, the pipeline of tasks into a graph, and then using this graph representation, we have a genetic algorithm that finds the optimal placement of each task in each device. So then we can have this optimized execution of the entire pipeline. So on the right side, we have the genetic algorithm that experiments different combinations of tasks in different devices, in different machines, like machine 1, machine 0. So it tests different combinations of execution of this task. So then it finds the optimal allocation of tasks. In that video, we see one of the executions of the algorithm. So the algorithm is testing where to execute each of the tasks. So it basically minimizes the costs of the RAM, of the CPU, of the network traffic. So to minimize these costs, it experiments different types of assignments, and when it finds it deploys the system. Now it restarted the animation, so we can see how it tests different associations of machine to a task. So when the association of a task to a different machine changes, the color here on the representation changes also. So it tests different associations of task of function block to a different machine, a different device. Okay, moving on to our last use case regarding zero make defects manufacturing. This use case aims to reduce the most possible the number of defects that we have in a shop floor, in an industry. And for that, we have different actions or different components that we can develop for this kind of systems. We can develop systems to detect defects. So these type of systems are like vision systems that at the end of the line you install and check if the product has a defect or not. So these are the kinds of systems that are developed for detection. So they are able to detect if you have a defect in the product or not. So this way to avoid to have the operator the entire shift looking for defects, because this is a hard task. Then, if you detect a defect, you can have different actions, other different components. You can repair the defect. That is the more typical action. But you can also have a different type of strategy. Instead of detecting the defects, you would aim also to predict. You would have a defect, because, for instance, imagine that you are able to detect a deviation in some sensor of the process that you have, you would be able to check that the machine is not working properly and detect that the machine will produce defects in a next period of time. So this is like the prediction prevention components that you can develop for this kind of system. You can develop a system that predicts when a defect will happen. So an algorithm that would analyze the data that is coming from the process and check if it has deviations or not. And based on that, on those deviations, detect if you will have a defect or not. And the prevention component that based on that prediction, I will suggest that you change the parameters of that machine. So you have these different components that you can develop for this type of system. So we, in a project called OpenZDM, that stands for Open Zero Defects Manufacturing, we developed a system that basically performs that kind of analysis. So in this diagram, you can see the execution of the algorithm. So we have a machine learning model, like a classifier, that receives a sample from the process, like every 30 seconds. And with that sample, if it predicts a defect in that sample, it provides an explanation of why we have this defect. So this explanation contains the variables that have more impact on the prediction of defects, so the operator can understand why the defect will happen. And we provide also a recipe recommendation, so to avoid that defect. So we provide an explanation together with a recommendation, so the operator can change the parameters on the machine, so he can basically avoid that defect. This was developed in the OpenZDM project. Let me just go back, because basically in the OpenZDM project we are working with Sonai Arauco that produces boards of wood panel boards. So they have different factories in Spain, in Portugal, in Germany, in South Africa, and basically Sonai aims to develop an algorithm to predict the defects before they happen. And the process where we are working on is the melamine process, melamine coating process, where we have a particle board that is basically the type of boards of the furniture that you buy on IKEA, of that particle wood boards. And then you have two sheets of paper that they glue to the particle board. And basically, this process of gluing the paper to the board and then pressing it at a high temperature and high pressure can cause defects on these boards that I will show you later, defects that it could cause. And one of the components that we aim to develop is basically this algorithm to predict when we have some deviation on a sensor, so we can avoid the machine to produce that defect. So here are some of the dashboards that we developed for this solution. We have the defect prediction dashboard on the top left side, where the type of defects that we predict for instance, broken paper that is the photo. So when the machine puts the paper with too speed, it could broke the paper, and because of that, it causes a defect. So we predict that type of defect. The final difference is basically a press error. So when we have a problem with the press, because for instance, imagine that the board stayed a lot of time on the press, so it produced a defective board. So we are predicting different types of defects. On the right side, we have the variables that have more impact on the prediction of the defect. On the middle part, we have the recommendation parameters. So we have the temperatures of the upper plate of the press and the lower plate, because the press has two different plates and they have different temperatures, around 214 degrees, the pressure, and basically some of the times of the process of producing these boards. So in that part, we recommend the parameters to change on the machine. On the bottom part, we have the model performance, because it is not only important to have the predictions, but also to know if the predictions are good or are not. So for that, we have two different percentages. That is the real defect percentage. That is, in the end, when I produce a lot of boards, I have like 1,000 boards being produced. I calculate the total of defects, and then I put in the platform this total of defects. So the real total of defects. So the real total of defects is around 6%, and the number of predictions, the percentage of predictions of defects is around 7%. So it's close one number to the other in that case. So overall, this is the dashboard for prediction and prevention of defects that we developed for Sona. This is another tool that we developed. It allows us to simulate new products. So imagine that I want to produce a new type of board. I can simulate here the characteristics of the board that I want to produce, the width, the length, the types of reference, the types of papers that I want to use. And then the simulation algorithm provides the recommendation machine parameters, so the temperatures to it, and provides also an explanation of why we provide these recommendation of parameters. Together with that, on the bottom, we provide also the estimated number of defects of the board. So before producing or starting producing this board, we have already an estimation of how many defective boards we will have. Regarding the other component that we developed a component also here on the OpenCDM project for defect detection. So we developed a vision system based on the NVIDIA Jetson Nano. So we have an NVIDIA Jetson Nano on that case and a camera. So basically, this is the inspection station of the board. The board is a quite large panel. It has 6 meters by 3, so it's quite large. And basically, currently, before using this vision system, the operator had to look to the entire board, that is a white board, for defects. I don't know if you can see, for defects like the ones that we have on this image on the left side. So we have on the left side one, we have some points. I don't know if you can see the points on the board, some black points that are some kind of defects that we have. And in the other image, we can see here also a defect that is a line that is more white than the rest of the panels. So these are two of the types of defects that they have on these panels. And basically, we aim to develop a vision system that we're able to detect this kind of defects. So this vision system was able to auxiliate the operator on the visualization or the inspection of the produced board, because this is a hard task for the operator. They need to be looking for very small defects, like 1 millimeter, in a very large panel. And during 15 minutes, this is okay, but after 15 minutes of working, looking for defects in a board like that, it's very difficult for the operators. And they make shifts for the tasks. So the operators don't like a lot making these tasks in the short. So because of that, we developed this system to run. So on the right side, you can see some of the results that we currently have there. So we developed a vision algorithm that uses YOLO. So it uses two YOLO models. One to segment the panel, and other to identify the defects on the panel. So as you can see on the right side image, we have identified the black dots on the panel. Here you can see some demo of the laboratory prototype that we currently have. So we have a vision system connected to, we have some samples of boards in the lab, and we have here developed the vision system, and we have the dashboard, the defects on the boards. So, in order to conclude some of the conclusions that we have in this talk, in this webinar, was that there are shifts in the strategy of the industries. So in the past, industries were a lot more reactive, both in the maintenance of components and also in the correction of defects. So we are moving from a reactive perspective for a more predictive and preventive strategy, where we predict and prevent failures before they happen, and we predict defects and we optimize the process a lot more than in the past. Then the second point is that the data that we collect from the shop floor and from the process is one of the enablers and the drivers for the shift in that strategy. So we basically need data and need good data to have this kind of algorithms. If you talk with someone that developed this kind of system, they will tell you that more than half of the journey is to have good data and good systems to let in data, because you are just able to implement those kind of systems if you have good data. But data is very, very complicated. The third topic is basically that automation and software configuration has a major role also in of nowadays and of the future. So in order to have more resilient systems and more fault-tolerant systems, the software configuration is one of the key points of the industry that we have. So the systems are able to continue to execute after a particular component fails. And as the last comment for this talk, I have that as I mentioned also before, that the integration of these components is the main goal of basically of this kind of systems. So for that, we need basically a transparent integration between the algorithms with the sensors, with the manufacturing execution systems, and with the other type of legacy systems. So we need a uniform integration so we can have this type of systems developed in the industry. With that, I finalize the talk for today. If you are interested in see more details and more information about what we work on, you can visit our website. This is the website of the Digital Lab, where you can see some of the work that we do, some of the open work jobs that we have. So if you are more interested in collaborate with us or with see more details about our projects, you can visit our website for more information. Thank you for your attention, and now I'm open to some questions.
Okay, so thank you for your attention. I know that we already passed through the last time because we started late, but we'll compensate next, okay, so you can leave early in the practical class. So we open the floor for some discussion, and if you have any questions, feel free to ask. I'm checking here online as well. I have two questions. I'm waiting for the students to put some questions. Do you have anything, any comments? Yes.
Fazer uma português, mas sim, que tipo de algoritmos é que usam frequentemente? Usam mais este tipo de classificadores, usam o reinforcement learning,
Utilizamos principalmente XGBoost, é um dos principais algoritmos que se okay. One of the main algorithms that we use is basically XGBoost because it has a lot of very good predictions. So for this kind of type of algorithms where we have a classifier, prediction classifier, we use like XGBoost, that is a very good algorithm that provides good predictions. We use also for predictive maintenance survival analysis algorithms that provide not only the prediction of remaining useful life, but also the survival function, that is a function that provides the probability of survival of a particular component that allow us to simulate the survival of the multiple components that we have in order to find the optimal time to replace all of them, or most of them. And we use also these optimization algorithms for problems of the optimization that we work on. So, like genetic algorithms, when we have some kind of combinatorial, like the task assignment problem. We use simulated annealing, for instance, when we have this optimization of parameters. So we need to find the optimal parameters of to put in a machine. And regarding reinforcement learning, we are trying now as next steps to use some sort of reinforcement learning algorithm to perform this allocation of tasks, so we can compare the reinforcement learning algorithm with the genetic algorithm that we currently have. So it is one of the next steps that we have here.
I'll put one question now. Regarding the dinosaur tool that you mentioned before, some teams here, they are using other types of tools to manage the data. Can you let us know what are the advantages of using dinosaur in comparison to other tools?
Yes, the most common tools that we see as alternatives to dinosaur, I don't know if those are the tools are Node-RED.
Yeah, most of them are using Node-RED. That's right.
Node-RED. Node-RED is a very useful tool and very easy to use tool. It has already implemented some blocks of MQTT, of integration with databases, so on and so forth. The main limitation that I saw some years ago was regarding when you want to have a distributed system. So Node-RED, if I'm correct, only executes on the device. So we don't have a separated user interface. So you need to install Node-RED on the system, and you are not able to have this distributed pipeline of blocks. At least from my knowledge, that was like 1 year, something ago. So this is the main limitation regarding dinosaur. When you want to have multiple devices, I think dinosaur and Fordiac is a better option. As you will have everything in one device, Node-RED, probably it's a more has more resources and more community, and it's a more mature solution than dinosaur. So when you have just one device, probably it's also a solution.
So for the perspective of distributed systems, we will have some limitations, you're saying. One more following also this type of questions regarding, well, looking at the architecture and technology stack that the students chose. You mentioned that in OpenZDM you use Streamlit as a dashboard.
Mm-hmm.
So what is your feedback about Streamlit? Because we have also Grafana and others. So students want to use the dashboard mainly for monitorization of the sensors, maybe do some control actions manually. So can you tell us your feedback about Streamlit?
Yeah, we mainly work with these two kinds of solution of Streamlit and Grafana. And from our perspective, when you have just monitorization, so when you are just collecting data, Grafana is very good. Grafana, you don't need to program anything to have like a dashboard working on. You just need to make the SQL queries on Grafana, and the interface is very easy to use of Grafana. The problem of using Grafana comes when you need some action from the dashboard on the business. For instance, if you want to have a button in Grafana to perform some action, you are not. At least it's difficult to make that. It's not straightforward to make a button or to put a button in Grafana.
If you need some interaction that is more than looking to the dashboard from the user, it's better to use Streamlit because it's not very difficult to work on. You need to program the interface. That's different from Grafana. With Grafana, you need just to install components and then it's everything working on. With Streamlit, you need to program the interface, but you have a lot of examples, so it's easier. So my suggestion would be if you have some sort of interaction from the user, like clicking in the button, filling some form, configuring something, it's better to use Streamlit. Otherwise, if it's just monitoring, use Grafana because it's a better and more simpler option, and it's also more resilient than Streamlit. It's just one.
Okay, so we have a little bit development overhead with Streamlit, but we have some benefits regarding the control and actions from the user. Great, so last chance for one additional comment or question at home also. If not, I guess that we can wrap up for today. Thank you very much, Eliseo, for your talk, and I'm sure that students will annoy you in the next couple. Thank you very much, guys.
Eu falei, vocês não usam cloud para distribuir. Como é cloud não é projeto? Tem coisas na cloud não é projeto?
Sim, aqui temos no caso do projeto do OpenLabs, a Sonai usa Microsoft Azure para integrar